Right, now I don't know about you folks, but I think a question like this is a real opportunity to get a bunch of marks, and all you've got to do is be careful. Remember your Subat equations, and there's not that much that can go wrong. You just need to be prepared to think it through. So I reckon it's well worth making a little sketch at the beginning of what's going on. So we've got a car, and we know its initial velocity is 0 because it starts from rest, and then in 20 seconds it's going to reach v velocity. So I'm going to put time equals 30 seconds, 20 seconds there I mean, and just going to put v there to show that that's the speed it's going. Then we're going to have a gap of another 30 seconds. So at t equals 50, the velocity is still the same. So now if I'm thinking about the next bit, I could say that the u at that point would be the same as the v from before. Then we're going into a bit where we've got an constant deceleration of a half a mile meter a second. So I'm going to write a equals minus a half meters per second there, and that's going to happen until the velocity is 8 meters per second. I'm not trying to work anything out here, I'm just saying, making sure I've got a real picture in my mind before I attempt to draw the graph. So then that's going to continue for another 15 seconds, and at that point my initial velocity for the next stage will be 8 meters per second, and then we're going to decelerate until we get to 0 meters a second, and that deceleration is going to happen at negative a third meters per second squared. Now I've done that, we can come across and maybe try and translate that into a velocity time graph. There's slightly more than one way you can do this, but what's important is that you do show the timings with what you know along the bottom. So you could go 20, 50, or you could just show the regions in between. So we get up to velocity v, and I'm just going to write velocity in meters per second there, and time in seconds there. And first up, we've got the first 20 seconds. Now, because we've got regions of time for a bit, it's probably easier to do the time like this and then say, right, we're going to have 30 seconds for the next bit. And then we don't know how long we're going to have for the first slowing section, so we could call that t, or I think in the mark scheme they actually say t1, so that's a nice word. But if you've used any letters or anything at all, it doesn't really matter. Then you've got 15 seconds for the next bit, and finally we have another round as we're going down to 0, which you could call the time 2, or if you've got a different letter, that's absolutely fine. So the first thing that happens is we should have something that looks just about like a straight line going up to the point at which we've got v there, and we've got 20 seconds there, and then that's carrying on, and I like to put in dotted lines going down there. They didn't show those in the mark scheme, but I think that's a good idea. And then we're going down, decelerating until we get to 8 meters per second. Now we don't know what that is, so I'm just going to guess it as being a half. It doesn't matter if yours is significantly different, as long as it shows it happening in the right way. So that's happening at that time. Then it flattens again and stays at 8 for 15 seconds. And then we have a time at which it's not going to be this next bit has to be less steep than the bit we had before, so I'm actually going to lengthen that to there. All right, and that's your 3 marks on that. Now finding the value of V. So that's part A. Well, if we use V equals U plus AT, we know that it's going to sorry, I'm jumping ahead. I was looking at part C. We don't need V equals U plus AT at all. We know that we have got, I'm going to start using we've got 140 meters represented in there, haven't we? And in order to work out, and that is the area of that, so I could say that 140 meters is going to be equal to 20 times V divided by 2. So if I halve that, that gives me 10V divided by 10, therefore V equals 14 meters per second. And then for part C, finding the value of V, we are going to be using that, because what I know is that my final velocity is going to be the value of V we've done, sorry, the total time taken. So the total time taken for the journey, we need to know this time and this time. So we now know that this is 14. So my U is 14 meters per second for here, and my V is 8. So using V equals U plus AT, I can say that final velocity is 8 is equal to 14 minus a half of t, so t over 2. So if I add t over 2 to both sides, or if I could double everything, couldn't I? 16 equals 28 minus t, so t equals 28, take 16, which is 12 seconds. So that's t1. I now know that that is 12. And then for this one, my V equals U plus AT again. This time my initial velocity is 8, my final velocity is 0, and I've got minus t over 3. So if I multiply by if I multiply by 3, I get 24. I've written that the wrong way around, haven't I? It's 0 there and 8 there, but 24 will be t there. So our total time is going to be 20 plus 30 plus 12 plus 15 plus 24, which all comes up to 101 seconds. Right, so finally the total distance. Well, the distance is going to be the area under the graph. So if I call the 5 different regions A, B, C, D and E, it's going to be A plus B plus C plus D plus E. We know A is 140, B, just area of a rectangle, 30 times 14, and C will be it's a trapezium, so it's a half. Add the parallel sides of 14 plus 8, multiply that by the perpendicular height, which is 12. Then we've got another rectangle here, so that's 15 times 8. And finally we've got a triangle, which is 8 times 24 over 2, slap all of that into your calculator, and you should have got 908 meters. And that's 13 marks for all of that, which I don't think's that nasty. So we finally reach the final question, and we just need to think about the fact that we will have tension pulling down at that point and then pulling up at that point and doing the same. So it's going to be T will be all of those points there. We've got friction pulling back. We have a force of 0.5 G going down there. We have a force of 0.8 G going down there. The acceleration of B, well, we know that U equals 0. We do not know the final velocity. We know that the distance is 0.4 meters. We know the time is 0.5 seconds. And we want to know the acceleration. So we're looking for a SUVAP formula that does not involve V. So that gives us S equals UT plus a half AT squared. Pop in 0.4, 0 times T means we can ignore that bit, and then we will have a half A times a half squared. So that means that 0.4 is going to be, well, that's a quarter, isn't it? A quarter times a half is an eighth, so A over 8. Therefore A equals 0.4 times 8, which is 3.2 meters per second squared. Now then, so that was part A. For part B, finding the tension in the string. Well, we're going to be using the fact that force equals MA. That's the force that's going to be generated by it going down at that speed. So that force, 0.8 G, take the tension, because we've got that pulling down, we've got the tension pulling back up, is all happening at MA, which is 0.8 multiplied by the acceleration, which is 3.2. If we add T to both sides and we take that away, that therefore we can put 0.8 times 9.8, take 0.8 times 3.2 is going to be equal to T, which is, if you pop that in, you get 5.28, but because the 9.8 value that we're using is to two significant figures, in this instance we should be leaving answers to two significant figures. So if you're using a value that's already two significant figures, you can't go further than that. So it's 5.3 newtons for part B. Now the value of F, again we are thinking about forces, mass times acceleration, and we know that the force, that the tension that's pulling this along is 5.3, and that has to be equal to the 0.5 times 3.2, which is what you'd get for that, plus the friction. So the friction is going to equal 5.3, take half of 3.2 is 1.6, is 3.7 newtons. And then all we've got to do is state how we've used the information that the string is inextensible. Well, our acceleration, which was 3.2 meters per second, we've used here, haven't we? And we've also used it up here, and that has been critical to us being able to work out what it is. If there was any stretch in it at all, then this would accelerate at a slightly different rate, or it would take a while for that to catch up to that bit, so it would be more immediate here than it would be there if it was stretchy. So what they're looking for is the acceleration of A is equal to the acceleration of B. You don't have to use the terms A and B. You can say both particles, the acceleration is equal. That's absolutely fine. Okay, time to jot up all of your marks and upload your evidence of what you've done, and let me know what your final score is. We're through that. And I will see you on Monday for some of you, and Tuesday for others, for us to start talking about where we go from here in terms of continuing to revise those parts of what we've done over both papers, the bits that you have found trickiest. So if you could come along to that, or if you've even done it before that, saying, right, these are the questions that really cause me trouble, if you could let me know before, then we can hit the ground running with that on our first lesson back. Marvellous. Cheerio, folks.